Hello guys, you're welcome to Nisiki Academia. If you're not subscribed to this channel, do well to hit the subscribe button and subscribe to enable you get notifications of our subsequent videos and of course our online classes. Alright, so in this video we're going to be looking at mathematical relations. Mathematical relations. So basically the keyword here is relations. Alright, the keyword here is relations. This is actually a subsection of the general topic relations and functions. We'll be looking at mathematical relations here in this video. All right, so basically we'll be looking at what a relation is. First of all, what is a relation? So a relation is a set of ordered pairs. A set of ordered pairs. When I say ordered pairs, I'm talking about ORDERED, ordered pairs. Okay, let's say x comma y, in which each element of a set X is assigned to elements in Y by a well-defined rule. All right. So by a well-defined rule. So when we have a set of ordered pairs in which elements of the general set X, okay, is assigned to elements of the set Y by a well-defined rule, that is by a well-defined criteria, then we call that a relation. Okay, so a relation on the pair x and y is denoted as x relation y. That is when you are relating the elements in set x. The elements in set x are denoted as small letter x, while the elements in set y are denoted as small letter y. So when you're trying to relate the elements in set x, which is this small letter x, with the element in set y, which is this small letter y, we say x relation y. All right, we say x relation y. So it means that x is related to y. That's what it means. So basically, there are different ways in which members of a particular set relates to members of other sets. There are different ways we can actually relate elements in set X to elements in set Y. Okay, so basically, we'll be looking at several examples to make it very clear. All right, so for instance, now we say let set X contain elements 1, 3, and 5. Okay, let set X contain elements 1, 3, and 5. Now, if we want to relate set X with itself, if we want to relate set X with itself, okay, we don't want to relate set X with Y. We want to see how we can relate set X with itself. Then we will say X times X. We will not say X relation X, because basically the relation has to do with elements in one set being related to elements in another set. So we say X times X. So now at this point, what we'll do is to relate every element in set X by themselves, okay, and by other elements in the same set X. What do I mean? First of all, we should understand that this particular set X has three elements, 1, 3, and 5. So we have to first of all relate the element 1 with itself, relate element 1 with 3, relate element 1 with 5. After that, we'll now come to 3. We'll relate element 3 with 1, relate element 3 with itself, then relate element 3 with 5. When we come to 5, we'll go to 1, 5, 3, 5, 5. So this is what we are saying. We'll create a set like this. Then we'll have this, say 1 comma 1. This is how we write it. Then we'll say comma 1 comma 3, comma again 1 comma 5. All right, then we are done with 1. Let's go to 3. Still in the same set, we are not differentiating it. We say 3 comma 1, 3 comma 3, then we have 3 comma 5. Ensure you separate them with comma. Then after that, you go to 5. You say 5 comma 1, 5 comma 3, then 5 comma 5. Then you close the set. Okay, so basically this is a set of X being related to itself. Just take note of that, that a particular set of ordered pairs can actually be related to itself. But majorly, relation talks about the relationship between elements in one set and elements in another set. All right. Okay. So if we want to actually make this completely a relation, remember that the definition is that a relation is a set of ordered pairs in which elements of a set X is assigned to elements in Y by a well-defined rule. So there must be a well-defined rule. There must be a well-defined rule. So now let us take for instance that the well-defined rule here is that x1 should be greater than or equal to x2, which means that in this set here that our x1 must be greater than or equal to x2. Let's call this x1, let's call this x2, x1 x2, x1 x2, x1 x2, x1 x2, like that. So a relation without a well-defined rule is not a relation. Okay, it's not a relation. So how then do we navigate through this to actually get the relation? So what it means is that you will only form a relation from this set based on this rule, and the rule states that the first value must either be greater than the second value or equal to the second value. So it means that all these things in the set are not what we need based on the rule, because the rule is that x1 must be greater than or equal to x2. So if we should follow this rule, what do? We will now say arrow equal to, then we'll come here and we'll pick the set of, or the pairs, let's call it pairs, the pairs of things here, the pairs of things here that follows this rule, that shows that your first value in a pair is either greater than or equal to the second value. So now let's check this one. Is this number greater than this number? No. But is it equal to it? Yes. So it means that we would say 1 comma 1. Let's go to the next one. Is this number greater? Is 1 greater than 3? No. Is 1 equal to 3? No as well. We'll leave that. Let's come here. Is 1 greater than 5? No. Is 1 equal to 5? No. Is 3 greater than 1? Yes. So we'll pick, we say 3 comma 1. I believe you're understanding. We'll go to the next one. Is 3 greater than 3? No. But is 3 equal to 3? Yes. So we'll say 3 comma 3. We'll go to the next one. Is 3 greater than 5? No. But is 3 equal to 5? No as well. Then we'll go to the next one. Is 5 greater than 1? Yes. So 5 comma 1. Okay. Then we'll go to the next one. Is 5 greater than 3? Yes. We say 5 comma 3. Is 5 greater than 5? No. But 5 is equal to 5, right? So we say 5 comma 5. Then we'll close. So it means that this is now a relation. This is now a relation. So that's the idea. That is the idea here. Okay, I believe it's clear. So there must be a well-defined rule, and the rule will be given to you. So the rule for this particular one is that x1 must be greater than and equal to x2. So if it's not greater than x2, it should be equal to x2. We saw some values in which 3 was not, is not greater than 3, but 3 is equals to 3. 5 is not greater than 5, but 5 is equals to 5. 1 is not greater than 1, but 1 is equals to 1. All right. So now let's look at another example. Let's look at example 2. Let's look at the second example. Now, let's say that we have A equals to 3, 4, 5, and 6. Then we have B to be equal to, let's say, 3, 6, 8, 9, 11, 14, 15, 16, 18, 19, and 20. Okay? And 20. All right. Then we have a rule. Okay. With the rule is that A relation B if and only if B is a multiple of A. Okay. It's a multiple of A. This is the well-defined rule that we should follow. So now let's solve this. So for us to achieve this relation, okay, we have been given the sets. All right, we have been given the sets. We have set A, we have set B. And this is a rule that is guiding what our relation. You say A relation B must be formed if and only if everything here is a multiple of everything here. But it's not even possible for everything here to be a multiple of. So what we'll do is to we'll check we'll check what is in set B that is a multiple of set A. All right, that is a multiple of set A. So that is simple. So one thing you need to note is that the rule that governs the relationship between set A and set B is governed, and it's actually dependent, is defined by this rule. All right, it's defined by this rule. Okay, so now what will be our relation? What will be our relation? Now, when we say multiple, what comes to mind? Now, the word multiple in this context, okay, you're talking about a value, okay, in this set B that would actually be divided by the values in set A without a remainder. Okay, the values in set B that will be divided by values in set A without a remainder. Okay, so basically we are having 3, 4, 5, and 6. Multiple B should be a multiple of A. Okay, B should be a multiple of A. So now, first of all, let us look at the different values, okay, that are in set A. We have 3, 4, 5, and 6. We have 3, 4, 5, and 6. So which values in set B can divide the values in set A and there will be no remainder? We want to now relate each element in set A by the elements in set B based on this rule. So now, since we are looking at A relation B, we are relating A with B. So it means that the values for A will have to come first before B. The rule is that we will now relate the values in set A by the values in set B that can actually divide the values in set A without a remainder. That's what we mean by multiple. B is a multiple of A. Okay, B is a multiple of A. So now let's go through that. So now let's start with 3. Let's start with 3. So now we'll look for numbers that can divide this 3 without a remainder. So now let's start with 3. So 3 comma, let's get the first pair. So now can 3 divide 3 without a remainder? Yes, because 3 divided by 3 is 1. All right, it's a whole number. There is no remainder. It's not like a decimal 1.2, 1.4, 1.5. So 3 divided by 3 is 1. So it means that 3 is a multiple of 3. So we say 3 comma 3. We'll go to the next one. Can 6 divide 3 without a remainder? Can 6 divide 3 without a remainder? Yes, 6 divided by 3 is 2. All right, 6 divided by 3 is 2. So we say 3 comma 6. Let's go to 8. Can 8 divide 3 without a remainder? Can 8 divide 3 without a remainder? No. 8 divided by 3 will give you a decimal. Okay, 8 divided by 3, 8 cannot divide 3. If 8 divides 3, you have a decimal value. There will be a remainder. So it means that one is not part of it. So now let's check 9. Can 9 divide 3 without a remainder? Yes. 9 can actually divide 3 without a remainder because 9 divided by 3 is 3. So we say 3 comma 9. Okay. So now let's check again. Can 11 divide 3? No. Can 14 divide 3? No. Can 15 divide 3? Yes. So we say 3 comma 15. All right. We are still going. No. Can 16 divide 3? Can 16 divide 3 without a remainder? No. Okay. 16 cannot divide 3 without a remainder. Okay. 8. Can 18 divide 3 without a remainder? Yes. So we say 3 comma 18 because 18 divided by 3 is 6. 6 times 3, 18. 3 times 6, 18. So they are multiple of themselves. All right. So can 19 divide 3 without a remainder? Okay. 19 divided by 3. Will there be a remainder? Yes, there will be a remainder. So they are not multiples. Can 20 divide 3? 20 can not divide 3 without a remainder. So it means that we are done with relating 3 with the multiples. Okay, we are done with relating 2. Now let's go to 4. Okay, so let's go to 4. So we remember we always separate it with a comma, so we now go to 4. Now is 3, okay, is 3 a multiple of 4? No. Can 6 divide 4? Can 6 divide 4 without a remainder? No. Can 8 divide 4 without a remainder? Yes. So 4 comma 8. Let's go to 9. Can 9 divide 4 without a remainder? No. 9 cannot divide 4 without a remainder. Can 11 divide 4 without a remainder? No. Okay. Can 14 divide 4 without a remainder? Can 14 divide 4 without a remainder? No. Can 15? No. Can 16? Yes. 16 can actually divide 4. Okay, because 4 times 4 is 16. So 4 comma 16. Can 18 divide 4 without a remainder? No. Can 19? No. Can 20 divide 4? Yes, because 20 divided by 4 is 5. So we say 4 comma 20. All right. So we are done with, I think we are done with 4. So now let's go to 5. Can 3 divide 5? No. Can 6 divide 5? 8 cannot divide 5. 9 cannot. 11, 14, 15 can. So the first one is 5 comma 15. Then can 18, can 16 go? No. 18, 19, 20. 20 can divide 5. 20 divided by 5 is 4. So we say 5 comma 20. All right, 5 comma 20. Then now that's all for 20. Let's go to 6. Okay, can 3 divide 6 without the remainder? No. 3 over 6 is 1 over 2, that is 0.5. 6 can divide itself. Okay, 6 can divide itself, so 6 comma 6. Okay, um can 8 divide 6? No. Can 9 divide 6? No. 11 cannot. 14 cannot. Okay, 15 also cannot. 16 cannot. 18 can, because 18 divided by 6 is 3. So we say 6 comma 18. 19 cannot. 20 cannot as well. So that's the end. All right, so this is the relation. So I had to take my time to explain this step by step so you will get it clearly. So it means that this is the relation of A and B, A relation B, based on this rule that B must be a multiple of A. All right, that B must be a multiple of A. So now let's look at the third example. We're looking at treating the third example quickly. All right, let's look at the third example. Now, let's say that A is equals to 1, 2, and 3. Okay, and B is equal to a rule that B is such that this dot dot here, this column means such that B is a natural number of 1 less than and equal to B less than and equal to 10. Okay, now we are being told, say, a relation obtain a relation arrow from A to B. Okay, when A relation B, if B is equal to 2A minus 1. All right, minus 1. Now all these things are just plenty English, just big English. All right, so how do we navigate through this? I'm going to be explaining it for you. Now, first of all, now solution. First of all, you must take note of the fact that A is equal to 1, 2, and 3. Okay, now we are not given set B, we have to now find set B. The rule for even getting set B, they are not even giving us a rule. We are being told that there is even a rule in getting B. So we are saying that the element of B must be a natural number in this interval. And what is the interval? The interval is that B, okay, is in between 1 and 10. But we must take note of these signs. Very important. Now, what are these signs? This is less than and equal to. This is also less than and equal to. Now, we are being told that 1 is less than and equal to B. And B is less than and equal to 10. Remember, left hand is less than and equal to greater than his right hand. So this less than because it's the left hand side. Now I want you to understand this. Now we are being told that 1 is less than and equal to b. So it means that b is greater than and equal to 1. You will not be able to clearly understand it by relating 1 with b. Rather, relate b with 1. And how do you do that? If we are saying that 1 is less than and equal to b, it means that b is greater than and equal to 1. It's very simple. If we for instance now we say 5 is less than 10, which is true, right? It's true that 5 is less than 10. So if 5 is less than 10, it means that 10 is greater than 5. That's what it means. Okay? So the best way to actually understand it is to relate when you are trying to interpret the interval, relate the variable with the constant on the left hand side. Then on the right hand side, you just relate it normally. Look at what I mean. We are saying that 1 is less than and equal to b. It means that b is greater than and equal to 1. It means that the values for b will have to start with values that are greater than and equal to 1. So if we are saying values that are greater than and equal to 1 to values that are less than and equal to 10, it means that we have to start from 1, because you see values that are greater than and equal to 1, that is greater than 1 and equal to 1. So values that are greater than 1 comes after 1. So it means that we are talking about 1. What are the other values that are greater than 1? 2, 3, 4. Then we have to take note of this. So we will not just write and be writing and become so excited. We have to take note of the other part of the interval that states that b should be less than and equal to 10. When we say b should be less than and equal to 10, it means that the values that would end this particular interval must not be more than 10. It must be less than 10 and even 10 as well. 10 is also inclusive. So it means that we'll have to say 4, 5, 6, 7, 8, 9. Then we'll stop at what? 10. Simple. Then we'll stop at 10. Okay? So what it clearly means is that these are the values for set B. Then we are being told that the relation from A to B must be that B is equals to 2A minus 1. It must be that B is equal to 2A minus 1. So we will now have to pick out of this set, we will now have to pick out only values that corresponds with this defined rule. Pick out only values that corresponds with this particular what? Rule, which is that 2A minus 1 should be B. Okay? So it means that